Okay, it looks like the microphone's working. Yeah. And then it's automatically recorded. So pause the recording. Good. Yeah, cool. All right. Hey, everyone. I'm Raj. I'm one of the ASIC Team co-directors. Thank you so much for coming out to our Asynchronous Circuits Workshop. This was born out of the idea of a paper reading, which Vishnu recommended. And now this is like a pretty awesome workshop that we kind of want to share with you all. So asynchronous circuits is a pretty unique topic. I feel like it hasn't really covered much. You guys can learn more about it. So yeah, I'll let you take it away.
Yeah, I think I'll just put the light from on. Okay. For now, and then we can go.
Okay, sure.
Yes.
Okay.
Hi guys. Yeah, thank you so much everyone for coming here. I know it's midterm season and everyone's busy, but thanks for taking out the time. And I promise you, like, this will be a new world view to to those of us who are used to the synchronous pipeline design, and it will definitely help you out in your amazing careers as a chip designer to build high performance circuits. Because when you want to do some novel architecture, just sticking to traditional systems barely ever helps. So one question I want to start off is, how many of you heard of asynchronous systems or circuits before this workshop? You've heard of it?
You said it last time, sorry.
Okay. Okay, from our ASIC team, right? Okay, awesome. Okay, looks like it's gonna be a novel topic for everyone. So let's get started. The first thing that I want to introduce here is the classic idea of pipeline. Now, how many of you have heard of pipeline? Okay, anyone wants to volunteer to explain what it is? No one? Okay, so the idea of pipelining, or the idea of making circuits go fast, is that you take some solid block of logic that is in the critical path. So it's the logic that consumes the most amount of time in your circuits, and then slice it up into small chunks like this, right? A simple analogy would be, if you guys are making cake at home, right? And let's say if it involves 10 steps, and it's just one of you, like just a single person, doing the whole 10 steps together. It's definitely going to take, let's say, and if each step was a clock cycle, right? It's going to take 10 clock cycles for you guys to get done, for a single person to get done. But how about this? You have 10 people, each one works on one step. They do it, and then they just move it to the front of them. Now that way, once your pipeline fills in, once everyone has some tasks to do, you're going to be shipping out one cake every clock cycle. Does that make sense? Right? So you can clearly see how building this pipelined approach makes things faster. So you can make more cakes per unit of time. Does that make sense? So essentially what you're hacking is, while one person is working on, let's say, mixing the, like the batter or cutting the fruits, the other person can go bake the previous cake, that he has gotten with it, right? So you're enabling concurrency, you're enabling parallelism, and pipelining is a way to do that. Awesome. Okay, so that's the classic pipeline, and this is how it's implemented in hardware. What we usually do is we take that. So what these reddish blocks that you see here are combinatorial blocks. Everyone aware of what is a combinatorial block? Yeah, thumbs up if you. Please let me, we have 2 hours with us. We can pause and you can ask any questions at any time, and we'll go step by step. No need to rush through it, okay? So what is a combinatorial block? Anyone wants to say?
It's basically made up of logic gates, like and or, right?
Right.
That can be done without a clock. It just happens.
Absolutely. And it doesn't have any memory aspect to it or time nature to it, right? But the thing is, you build memory circuits out of these combinatorial circuits itself, right? If you ever zoom into a latch or a flip-flop and see, it's made up of gates, combinatorial gates, just in a clever way, with a feedback loop. And that feedback loop is what brings memory to systems as well as to our brains. So if you see, either be it intentional or unintentional, we have built the whole world as humans around us, taking inspiration from the systems that we are fundamentally. So we've built circuits like, how our neurons are. There is a famous paper. It's by McCulloch and Pitts. Back in the days, it's actually back in the 1900s. I think it's 1945 or something. It was the first ever paper on neural networks. That's what started off neural networks. And their whole paper, if you read through it, if you follow the mathematics of it, it's essentially them trying to prove that our human neurons and the way it's wired up together perform exactly the same function as logic gates, right? So now in terms of memory, where does that come? How do we remember? Data in our head, right? You have neurons, and then let's say you have an experience. There are, for that particular type of experience, you have a specific loop that's formed in your head, and those neurons keep like one spikes, and that spike travels around the loop and keeps reinforcing itself. So that's how those neurons remember a specific value. And guess how flip-flops remember values? You have a gate, you feed in a value into it, it feeds back into another gate and keeps reinforcing it, right? So that's a parallel. So we humans have built the whole world of circuits, like digital systems, knowingly, unknowingly taking inspiration from us. But one thing we don't have in our head is some kind of clock that's always ticking. We don't have that. Yes, we do have like circadian rhythm and things like that. But those are like global clocks, or like there's no. If you just look at our neural activity, is there any clock that guides how different activations are? No, right? Like, can we say that our brain is like 1 gigahertz of frequency or 10 gigahertz of frequency? No, because there's no notion of a clock in our brain. Our brain is fundamentally asynchronous. So people ask the question, then why do we build synchronous circuit? Like, why don't we copy that idea onto circuits? It's more closer to our brain, and that's how asynchronous circuits were born. So this is a classic pipelining idea. We saw how this, and this is what most of the designers do to immediately increase the speed of any processor. They take that combinatorial circuit in the critical path, slice it, and then pretty much our cake example, they can bake more cakes per unit time. But what we're going to learn is black magic on how to make even this go faster. So for that, we'll do a small activity right now. And this activity will involve simulating the pipeline, asynchronous as well as asynchronous pipeline using these chairs. And it's a simple game. You can see here 2 chairs, 5 chairs, and 1 chair. Now these chairs represent combinatorial logic, right? Propagation delay and combinatorial logic. Everyone is clear with what is propagation delay and combinatorial logic? Okay, so propagation, if you take an AND gate, right, or any gate, you flick its input, how much time will it take before the output flicks or responds to the input flick? That's a propagation delay. So pretty much how much does an event take to propagate from the input of the gate to the output? So fatter gates take a longer time to propagate an input, right? When I say fatter gates, means gates on the old nodes, like 120 nanometers and stuff, 180 nanometers, like the fatter the feature size, the slower it is, right? And that's why people are mad behind trying to get smaller and smaller transistors. Although there's a saturation now, there's a recent Nobel Prize that people want for quantum tunneling in the physics, which seems to unlock some area of some quantum tunneling effects or something like that, which I don't even know about what they are, but what is happening is we're saturating at 2 nanometers right now because of the quantum tunneling effects, right? Charges leak through the gate, and it's not really a transistor anymore at that point. But anything, deviations aside, the smaller the smaller your gate is in terms of feature size, or in terms of number of transistors, the lesser the propagation delay. Okay, so over here, this might represent some kind of multiplier or adder that has 5 chairs placed across it. So this one will have the maximum propagation delay compared to the other 2. So what we're going to do is we're going to simulate it. Any volunteer for this particular game? I will explain the rules. Okay, there's 2 people. You want to? Okay, there's 3 people we have. Okay, that's we need 3 people in total. So 1, 2. You guys raise your hands first, and yeah, I saw your hand third. So 3 people. Yeah, no, you as well. Yeah.
That up so you can show this.
Sure.
Okay.
Awesome. So first, we're gonna do a synchronous pipeline, all right? And what's your name?
Robert.
Robert. Okay, so Robert's gonna be the player for the first round. Where's the? Yeah. So the idea is that you're gonna be taking this wheel, all right, and then putting it into the top, and then transferring it, like just literally pouring it out, and then like pouring it out sequentially, all right. But there's a small caveat to it, which is you can only do this operation in each stage, until you hear a click. If you are doing that operation, and let's say like for example you're in the middle, and then you hear a click, you're disqualified. Oh, yeah, right. Okay, so that's where you lose. Like that's the depth of the data packet, which is
No problem.
yeah. So it's like so that's the game. Do you understand the game? So I will be simulating the clock.
Yeah.
Okay, and it'll be through a tick. Okay, everyone knows what's a passage in a clock. Everyone knows what's a clock.
Yeah.
Okay, yeah. So a clock signal is simple. Let me just show you. So I know some of you did nod your head. This is a clock signal in a digital circuit. It's just an oscillator. It's like 1 0 1 0 1 0. Okay, that's a clock in a digital circuit. Outside just the edge that runs from low voltage level to a high voltage level, and that edge is just a falling. Okay, and in a typical pipeline like this, these are flip-flops. They'll only latch in data. When I say latch in, they'll only register the data when they're on a passage. Does that make sense? Okay, so we will be simulating passage through clicks, all right? And I will be timing it. If anyone is interested, okay, this you can see it right in front of your eyes right now. How much slower is synchronous pipelines compared to asynchronous pipelines? What you can do, you can stop the timer when he starts the game, and you can end it when he gets his wheel across all over here. Okay, and then keep a record of that time. All right. You can do it on your phone as well, but I will be taking a note of it as well. Okay.
So only start by saying like, only do everything with snaps.
Yeah, exactly. So first, let's start with a sample snap period. I'm gonna do 2 seconds, at like one click every 2 seconds. Okay. Take your time. Don't rush. Okay. All right. Let's keep it for a second because I don't have much dexterity to like tap it every 2 seconds. All right, 3, 2, 1.
Oh, I should go.
No, you can only move ahead when you hear a clock cycle. Okay, so that's you're disqualified. Let's let's go for another round. So what's my like? We're in the takes too fast. Like I just clicked before it could even move stuff through, right? I clicked once every 4 seconds. 4 seconds were clearly not enough.
You guys just
Well, I mean, you can have like bad circuits, bad transistors exist, right? But it's the designer's, it's the architect's responsibility to make sure that they perform well. Because there's nothing called a bad transistor. It's just bad architecture, right? So please suggest that time period that we can. So I did 4 seconds, once every 4 seconds. Can someone suggest it? 1. 1? That'll be too bad. You won't even get through the first.
I think like 5 or 10.
Yeah, 5.
Yeah.
Okay. 10?
Yeah, sure. Let's do 10 seconds.
Okay. Once every 10 seconds. All right.
Robert, lock in.
Okay. 10. Okay. 3, 2, 1.
Oh,
No.
wait.
No, you can like every stage you can. Only like only over here you pause. Like keep going. Okay. Done. Like it's all. 10 seconds are still not enough. Guys, suggest another accurate time. Let's see who gets it.
20 seconds.
20 seconds. Okay, 20 seconds per stage. 3, 2, 1, start. You can put it out of your hand. Don't worry. You don't need to necessarily put it like that. Okay, 20 seconds. No. Keep a watch for him. Like, look at how much time he's wasting after completing his task. Or we're meeting. Thanks, man. Let's lock it here. Okay. That's okay. Interrupts are there. Okay. All right. So he took like 40 seconds in total to complete his class. All right. So good job, Robert. Thank you. So Robert applied a synchronous approach. We still need you. So 40 seconds was Robert's record. Now what we're gonna do is we're gonna do asynchronous circuits. Okay. So we need 3 people. One standing at each edge, like flip flop here. One like take the gap. Take the gap. Yeah, you can come here. Yeah, what's your name?
Albert.
Albert, nice meeting you. And yeah, awesome. All right. So now what you're gonna do is you're not gonna wait for any ticks, nothing. All you're gonna do is take your time. You know, it's like a relay race. Just get it through. And once you're here, just give it to him, give him a handshake like that. And then you can just move on, give him a handshake, and then just keep going. Don't wait for any ticks. Okay. Awesome.
So once I get there, let's take it out.
Take it out and give it to him, right? And give him a handshake just as a gesture of, like a good. Yeah, it's like you don't want to massage.
And don't wait.
No waiting for any ticks. All right. Your time starts now.
Oh, what? What do you do?
I'm trying. All right. Awesome. So I'm gonna stop it. 20 seconds. 20 seconds
This time.
for this. Okay. Thank you so much. So guys, for the biggest hitter, like how we always do, like let's do a little bit of debrief on the engineering problem that we solved right now. In the first case, you saw a synchronous circuit, right? Because you could only move when the clock ticked, right? And then the period of the clock, right? What is the period of the clock? The breadth of this, right? Like the length of this each cycle, like the time period, had to accommodate for the worst case delay, right? So it took Robert like, probably like 15 seconds or something to get through this big part. But the thing is, you can't have waiting periods in clocks, right? Like you need to tune it to one frequency, and it has to be that. So he wasted like this probably took him like just 2 seconds, and he wasted 13 seconds just waiting, or he wasted 13 seconds waiting there. Sorry, that's a better example. But in the second case, when you didn't wait for anything, and when you just acted then and there, when you had bias towards action as opposed to someone telling you to do it, you just went through. The performance improvement was like when Snehal and I simulated this like before, just in a computer lab. I mean, we achieved only like about 15 to 20% improvement, but over here we had like 50% improvement, right? Like literally, I mean, not 50, 200% improvement. We doubled the time. Sorry. So isn't that? And what was the reason behind it? If you guys anyone can like quickly summarize it. Like, why did asynchronous movement of this data work faster? Yeah, go ahead.
That's mainly because if normal clocks are a standard amount of time for each one, then you don't really work everything's around the same amount of time.
Right.
Since clearly it weren't, you basically take the worst case, and everything is as long as the worst case.
Right. Exactly. Right. You agree with that?
Yeah.
Or you want to add on something?
It's just that one you're waiting for the process and the other not waiting for.
Exactly. You were not waiting for the process. So in all these so-called idle time, when these flip-flops move things right at this pass edge. Yeah, sure, there is a hold time here. Like if you guys have heard of hold time, set up a hold time, right? It's just the timing parameter, so don't worry, you're not missing out on a lot. Everything else before the next pass edge is just idle time. It's just sitting idly, right? Not doing any work. So you can see that with Robert, he finished it fast, and then he just he was dying to move forward, but the clock didn't allow him. So this whole clocked idea of the clocked world is super restrictive. It's super simple at first, right? It looks like, oh, I just clock everything and let the EDA tools take care of it. But you see how much of a performance killer it is. So weird. And the second case, when you saw how to make these like local handshakes, this concurrency and this nice collaboration, as opposed to some dictatorial, like things move faster, right? Like clock bang. So so that's the difference between a synchronous pipeline and an asynchronous pipeline, where you have people that are actually being concurrent and not waiting for any clock tick. So to sum it up, the average worst case delay, which is nothing but the average time it takes for one data token to move from one end to another, reduces because a lot of idle time is actually being cut down in these asynchronous circuits. Does that make sense? Right? And the activity was clear, right? Fantastic. So now, welcome guys to the world of asynchronous circuits. And in today's like the technical side of the discussion, we're going to see two-phase protocol, what it is, Mueller C elements, event-driven registers, a full-fledged pipeline, and then some application and results, and some next steps from where you can take this and apply in your real life, right? So we talked about this fancy idea and like, oh, there are handshakes and all of that, but how do we build these circuits? Okay, so let's look at that. This is called the two-phase communication protocol. So there are two lines here. Okay, first of all, in these asynchronous circuits, we look at something called events. All right, what are these events? Events are any transitions. Okay, so what are transitions? Anything that goes from a 0 to 1. Okay, or from a 1 to 0. Like anything, any flick is an event. It's a transition. Okay, and this approach was first proposed by Ivan Sutherland. He's 91 years old today. Extremely famous computer engineer. He originally wanted to speed up systems for performing aerodynamic simulation. I think for like some kind of like defense companies, he wanted to make computers faster. And then there was no way for him to do that with the synchronous world, because the best thing you can get with the synchronous world is like pipelining, right? And like, breaking things into those registers and trying to like increase the clock speed. But he found that, okay, something might be missing here. And he said, let's throw the clock out. There's literally a paper titled The Tyranny of a Clock. Like that, like it's the dictatorial nature of a clock. Puts a lot of overhead in your brains, and like it just like stops you from thinking beyond what can happen without a clock. So he's like, let me throw it out. And then he worked a lot on developing these circuits based on David Mueller's work. David Mueller is the forefather of these asynchronous logic. And he got a Turing Award, and he presented this. He didn't get a Turing Award for this, but he got a Turing Award for his software contributions. But he presented this in his Turing Award lecture, and ever since then, like it's a completely new worldview with asynchronous circuits. Okay, and the first thing that he came up with is called the two-phase communication protocol. So he figured out that you need two lines in the control path to move data forward. And what are these two lines? Request and acknowledge. And we use transitions, as I said, or events, as I said. So let's follow this really simple protocol. Please stop me if you have a doubt anywhere. You have a data packet coming in, all right? So that's D0. And then what you do is once your data is stable on the data line, okay? What do I mean by stable on the data line? Data lines are at the end of the day wires, right? Wires, right? Like when you connect to circuits, everyone has played around with Arduino, right? You have like, have you used I2C to communicate with two components? Okay, any kind of like communication, like have you used any communication between two devices? Okay, yeah, so like not wireless, like wired communication. Yeah. Oh, so you have some data lines, right? And the thing is, the data lines are at the end of the day wires, and the wires have like capacitances in them, right? Wires they are transmission lines at the end of the day, and they have it has some amount of capacitor. Like you and I, we have capacitances, right? So wires also have capacitance. So you need to make sure that you charge up these wires to a specific voltage level. So let's say you want to send one from this place to that place, you need to make sure that that one that that voltage that you rise here propagates enough. It has enough time to propagate and also raise, right? You get what I'm saying? If you swing a rope, the weight takes some time to move forward, right? Exact same idea. When you raise the voltage level, it takes some time to propagate to the from the sender to the receiver and become stable. Okay, that's what we're showing at step 1. So you put the data on the data line and make it get stable. Once it gets stable, you tell the receiver that, hey, this is I put a data. You request the receiver to latch it in, to store it. So you create an event, which is in this case like a 0 to 1 transition. But this is also equally an event, which we will see. there's no difference in this two-phase communication protocol. There's no difference between 0 to 1 or 1 to 0 transition. Okay, it means the same. And it's like the circuits are active on both these edges. So you have a request, you send a request event, and then you wait for the receiver to have acknowledged, right? It's common sense, right? Like you need to, like, for example, like Albert waited for Robert to receive the package, right? To receive the wheel before moving forward, right? And how do you signify that you have received the wheel? You give an event back, okay? All right, so you give an event back. And then once your event is given back, that's the third step, like acknowledge event is given back. You go back again and you're ready for the next data transmissions, okay? And you don't need to wait for another, like in this two-phase communication variant, like you don't need to wait for like this to come back down, because each of these lines coming back down is an event again by itself, okay? So you have the next data, you place it, the receiver places it, waits for it to nicely get to the other end of the receiver, like, and then signifies to the receiver that, hey, it's time for you to latch it in, and then sends an event, and the receiver receives it, clocks it in. Once everything is stable and it's like, okay, now I'm ready to let the data line go off, it clicks back again, and then the master it's better to use sender receiver. I'm just used to using master and something else, but yeah, anyways. So here, so here you have like the next data packet that you can send. Okay, is this clear to everyone? This is important. Any doubts here? Let's clarify it right now. Yeah.
What happened or
When does which the data packet?
number 3?
Number 3, yeah. So you put the you've taken a data packet, you put it on a data line. That's number 1. And then once you put it on the data line, you're like the sender is telling the receiver clock it in. There's no clock here. Like latch it in. Okay. So you send an event, and once that is done, the receiver needs to tell the sender, hey, I have clocked it in. You can get ready for sending me the next data, and that's what 3 is. Does that make sense?
So it's the request trigger the acknowledge.
So the request is triggered, and once the request is triggered by the master or sender, and then the acknowledge is triggered by the receiver. Okay. Does that make sense?
Yeah.
Right. The only rule is though, if the sender is saying 0 to 1 is an event, like if it did 0 to 1, your receiver should also do a 0 to 1. Okay. So the type of event needs to be the same. Like otherwise, like if it's like if this is saying hello, this should say hi. If this is saying hello, you shouldn't say like bonjour in French or something like that. That's like you need to make sure that like you speak the same language, right? So that's what the type of events mean. Okay. So these are transitions, and you use these transitions to send data. This is a simple protocol to understand. Everyone gets it? Yeah, go ahead.
Random questions, but like, so like for the sender, right? It's waiting for the receiver's acknowledgement.
Mhm.
There are some cases where the issue with the receiver on the sender's or sorry, receiver side,
Right.
You have like deadlock, for example, like you have a ship register,
Right.
You have new data, like, and there's like something blocking on the side, like
Right.
your system entirely stopped.
Mhm.
So like normally the clocks are just kind of override, but here is like the whole system stopped.
Yeah, so what will happen is if the receiver is having some issue, it won't acknowledge first of all. So the sender won't it's not allowed to change the data line. It'll keep the same data until the sender actually launches in. Does that make sense? It'll just freeze. The system will freeze. In clocked systems, if you for example, there's a protocol called AXI, right? And AXI uses a clock, right? But it does it it's like the way AXI does this is eating like this. Well, you can just eat like this, right? Because it has a clock, and it also has something called ready valid instead of request acknowledge, right? And it has to put the data. It puts the data in the line, right? Pulls valid up, like key valid. That's the actual signal, and then it waits for the the receiver to pull valid ready up as well. And once they're both high on a clock cycle, it's considered a successful transmission, and then it changes the data on the next pos edge. You have to have a finite state machine to do all those transitions. So it's really like eating like this, right? While with this, it's like just like, bro, I'm sending a request. Wait until like don't like respond to me with the same click. That's it. You don't need to wait for any clock cycles, Foxedge alignment, nothing. Just literally like if I click, you click. Done. Does that make sense?
Yeah.
Cool. All right, guys, everyone clear on this? Let's move on to the next one. Okay, so now how do you implement these? Like how do you build it into hardware? And that's where a special element comes in, right? Like this is like actual black magic. So this is called the Mueller-C element. Has anyone seen this before? What's like a C Mueller element? It's named after David Mueller, as I told you, the forefather of asynchronous circuits, because I think he's the one who invented this as well. And yeah, so what it looks like, what does it look like? An AND gate, a special AND gate, right? So this is like a Mueller-C element is nothing but an AND gate for events. Remember what I told events are? Any transitions, right? 0 to 1, 1 to 0, all of them are events. So this AND gates events, like what does that mean? Let's take a look at it. Let's take a look at the truth table, right? Keep a note of the, yeah, okay. So keep a note of the inputs and the outputs so you can map it to the truth table. So, there's, I think I'm talking over the 0. Yeah, there we go. So, you have like the blunt face is no event, and the smiley face is like activity. No, there's event. All right. So let's look here. If you have no event on both the on A and B, you get 0. If you have I mean, sorry. So if you have an event on both the lines, you get a 1. Okay. If you have no event, right? Like I mean, sorry, that's not the right way to put it. Like, so when you say 0, right, something has to come to 0, right? That's like it has to be 1 before and then come to 0. That's what I mean here by transitions. Okay. So when both of the lines settle from 1 to 0, it writes to the output 0. When both of the lines go from 0 to 1, it writes 1 to the output. All right. When any one of them is mismatched, right? Like when one transitions and another one doesn't, it just retains the previous value that it has in it. Okay. All right. So it'll be more clear when I show the circuits. This is just a small tweak to the Mueller-C element. You add a NOT gate here. Okay. Now, before I told you, if you have in the previous truth table, we saw that both of the input lines need to settle to the same value for that value to be written. Like both of them need to settle to 0 for 0 to come on the output. For both of them should settle to 1 for 1 to come on the output. Otherwise, it's remembered. But over here, if you're not one line, what ends up happening is both of them need to settle to opposite values for the A value to come through. Okay, so if A and B are mismatched, A's value goes through, right? Not this way. If B and A are mismatched, like if A is 0 and B is 1, like 0 goes through. Okay. But if both of them are same, A is 0 and B is 0, or A is 1, I mean A is 0, B is 0, and A is 1 and B is 1, nothing goes through. The previous values retain. So it's just a little bit of a tweak on the traditional behavior of a Mueller-C element. Okay. Pause me again whenever you have any doubt. So that's the truth table. You can see that only when there's like that, right? There's it writes that through. Otherwise, it retains the values. Okay. Let's look at the circuit implementation. This is the circuit implementation of this particular Mueller-C element. Okay, this flavor of it. Awesome. All right, guys. What circuit components do we have here? Okay, sorry. Good job. Someone said a D latch. Yeah, this is you traditionally built into latches, but I'm showing a flip-flop variant. So this is something that I designed out because it's easier you don't get latches that easily on FPGAs until you tweak their configuration like the bit stream, not the bit stream. Like there's a configuration set of bits that you have to have, but D-flops are more common, right? And so I'm just using D-flops as an example. You can build it using D-flops. It's just that you have to hack the clock line a bit. And then there's a delay line. Delay is a buffer. Okay. So anyone wants to map out the behavior of this? Wants to volunteer? But someone like you got it? Like I heard. Okay, fine.
Yeah.
Okay, sure. Okay, let's go through it step by step and be in synchronous with me, in sync with me, okay, for this, only for this, not with nuclear circuits, because we're doing asynchronous. So here, so let's say A and B are both 0. What's going to be the output of the XOR gate? 0, right? So is 0 like, this is a pause edge triggered flip flop. Is it going to move anything into, is it going to move A into it? So what will be the output? The output will be whatever value was in before, right? Right? If A and B are 1, still retains the value?
Yeah.
Aren't we getting this behavior already? Right? Yeah. Now, let's see when A is 0 and B is 1. What will be there'll be a transition here, right? From 0 to 1, right? Right? And then what will go through the flip flop? What will go through the flip flop? Clock will go through the flip flop? There's no clock here. No, that's not a NOT gate. That's just like a buffer. The thing is, like you need a slight bit of delay to meet. Like that's just for like meeting some timing. Like when you're building it in real life, like the CAD tools usually add these like timings, but you need, I mean, just for safety, I'm like not just saying giving this. So just consider it as A being connected to D. Okay, so it does that delay does nothing to it other than just like just delaying the value, the transition by a bit. Okay, it's just for like some timing. Like if we talk about the timing, like it's a little bit more of an in-depth topic. We'll keep it for another discussion. But for now, let's look at the functionality of it. Yeah. So all right, guys, are you following me here?
Yes.
Okay. So A is 0 and B is 1. What goes through the flip flop? 0 goes through the flip flop. A is 1, B is 0. What goes through the flip flop? So when there is a mismatch between them, the A value gets through, right? It just it just gets through, right? And it's driven by the circuit. So we have achieved the behavior of this flavor of similar element using this circuitry. Now, if you open it up, for those guys who are interested in the CMOS implementations of it, do you guys recognize this?
No,
You're doing diodes now? Okay, so this is for your future courses, and for those who are doing like digital electronics, like 334, might be familiar. So what this is I'm just gonna, take a screenshot of, like a brain shot of this, and then you can discuss it in your future courses. That's a pull-up network, pull-down network. Can anyone tell me what MOSFET is that?
What's
A PMOS, yeah. Okay, guys, so that's the pull-up network. This is the pull-down network. This looks like a weird. For those who did 334, you usually have, if the pull-up network is in series, your pull-down network is in parallel, right? Right. But over here, you see like both of them are in series. Like that's the common law. Like it's like wait, because it comes from like what's that? De Morgan's law. It comes from that, and like you to get like functional equivalence, you have to like do that kind of implementations. But we are building like some black magic, so we have to do some black magic stuff, and that's why we do this. If you work out the truth table for this, it will work out. What you see here. Okay, can someone tell me this? It should be fairly straightforward. What is this inverter loop you see here?
The light.
The light.
The light. Oh, sorry.
Whenever there's a loop, what did I tell you before in the starting of the meeting? It's storing information, right? So essentially, this is just like a simple implementation of it's not a flip flop. It's just a simple implementation of a memory. Okay, so this is a practical circuit that you can build. If you want to build it with MOSFETs, go for this. Each of these AND gates, NOT gates, will be expanded into how many transistors? Any 3, 3, 4 persons, 2 transistors. So that's like 2 plus 2, 4 transistors, and this is 4 transistors. This is an 8 transistor implementation. Okay, and this is the original implementation that Ivan Sutherland proposed in his paper. Okay, so just for your reference. But we will stick with just this idea for now. And by the way, you can implement similar elements in your own way. Like this, don't get like this might be stupid at a system level. Like don't fall prey for these things. As I told you before, as an architect, never the worst thing that you can ever do is be bound to a particular system of thinking and get saturated over there. So if you feel there is a way to like break out of it and find some new way to make a similar implementation, go for it. You might achieve it in like much less transistors than anyone that has done in history. Go ahead. What's your question?
So A and B, they're data.
A and B are just two signals. Okay, for now. We'll see how all of this becomes like control signals just a few slides ahead. For now, it's just like two inputs into a gate. Okay. Okay, for now.
You want to achieve the output when A and B are like all about things.
Exactly. So that's the classic similar. When A and B set into the same values, you want that value to go on the output. But in our small NOT gating that we did here, remember? There, that small bubble that you see here, it just flips the behavior. Like when both of them are opposite values of each other, A goes through, right?
That's why the next.
Yeah, that's why. Yeah, exactly.
Balance.
Okay. Yeah, no problem. Okay, good question. Let's move on. So now, using these similar elements, you can build a control path. Is everyone familiar with what's a control path and what's a data path? Right? Okay. Any questions there? Okay. Are you guys like CS students or something?
No, well, first year electrical engineer.
Okay. Awesome. I love that. Okay, that's fantastic. So a control path essentially gives signals for orchestrating the movement of data packets in the data path. Okay, so, to simply put. Okay, so data is actually like in an orchestra you have the conductors like doing this. That's essentially the control path's job. And then you have the instrument players like going full on. That's the data path. They do the actual that's where the actual stuff moves through. And then the orchestrator does all make sure that all of it is in sync and they don't crash into each other and all of that. So that's the difference between control path and data path. Does that make sense? Cool. So first we're building the control path and then we can build the data path. Control path is this. What it is just a bunch of weirdly connected similar elements. Now I'm just giving a small warning ahead. You'll have to take a look at it. I did give a warning. Oh my God. I'm just taking a note of the time, so I'll go to. All right, guys. So yeah, it will take a little bit of getting used to these circuits. So try to build one yourself, and that's the best way to learn it. But for now, bear with me, and let's go through this manually. Okay. All right. So we have connected similar elements in a weird way, and what are we trying to achieve through this? You have two signals: request and acknowledge. You guys remember request and acknowledge from before? Yes. Right? So let's say you have a request. Let's say all of these simulars are also memory elements. They have a memory element inside, right? Remember the implementation we have a flip-flop? Okay. All right, guys, this is going to be intense. Let's keep let's say all of these things were every single signal here and every single wire that you see here, right? Which and its driver, right? Which are these gates, like these elements. Let's say all of them are 0 first, like literally no value. Okay. Okay. And let's say you create an event. What is an event again? A 0 to 1, right? So let's create a 0 to 1 event. You create a 0 to 1 on the first similar here. What happens?
A 1 goes through.
A 1 goes through?
Yeah.
Where does the 1 go through? First of all, it comes out on the acknowledge first, right? So do you see that like from a standard?
Yeah. Like
you will get an acknowledge here, okay? That 1 will go through here, right? This is just a delay, okay? Yeah. For timing again.
Yeah.
So I'll explain what this delay is for just in a bit. You'll have the 1 come through here. What happens here? a one comes through, goes up, one goes there, right? Does anything happen to that similar when that line settles to a one?
Wait,
Yeah, who said yeah?
yeah, the why?
Why? Doesn't change.
Y doesn't change, right?
Yeah, it does.
So nothing happens to the output here,
Still a
okay?
one.
It's still a one. But you will have that one also go through here, right? What happens?
One. One again.
And outside, right? Until you drive this acknowledge back. Now, let's say, okay, you've driven one out there, right? What was the value of this zero, right? Now the zero is, let's say you transition back, right? You're giving an acknowledge. Nothing, like, does it go through back this way? No, right? Our similars are blocked, okay? So the thing is, you saw how the basic idea here is that you trigger a one on one side and it just like whips through the whole thing and gets all the way to the receiver, right? Does that make sense?
Yeah.
Okay. Please pause me if it doesn't make sense, okay?
It also gets to the. Oh,
So the acknowledge though, like once you have the request, having like once it gets through, right? You will have your acknowledge, but we will see that like you need to give an acknowledge from the receiver. What happens when you don't give an acknowledge is that when you create another event, right? It won't get through. Like it won't like whip through. Okay. So let's see that actually. I think it's a better idea to see that on the blackboard.
but my question is, it says acknowledge out on the left side.
Oh, yeah, so that's because this is exactly from these are conventions of the paper. Oh, I'm stupid. It should be acknowledging. Yeah, this is it's because that's acknowledge out. It doesn't mean it's the output, it's just that like, by the way, all the inputs are color coded. If anyone is like having accessibility challenge with the color, I can just point it out. I'll just point it out just in case. Because there's a request, that's the input, and that's the input into the system, and this is the output. Okay, this is supposed to be acknowledge in, but it sounds like it's an input, but it's not an input, it's an output. Okay, for those, I mean, like the blue colors are inputs and red colors are outputs. Okay, so let's actually look at this on the board. It'll be better. Can I use the?
Yeah.
We're on the board. Well, yeah, so we will. Any volunteers for this activity, or should I just do it myself? Anyone wants to volunteer? Event tracing through like a asynchronous pipeline. Okay, pull up. Yeah, yeah, you were first. I saw your hand first.
Yeah. You. No, you are.
Whoever gets it right will get a free paper cup.
Where's the thing?
Okay, I don't know how to get this rid of the screen. They're just like. Projective control. Okay, yeah. Or well, I'll switch on the back again. Okay, so first of all, let's draw the circuits, right? And then let's trace it. All right, guys, we're gonna have a 4-stage pipeline, a singular element, right? Then you have this. You have acknowledge in, which is actually an output, and then you have request in, which is actually an input, and then you have this thing going to a singular element again. Right? There's a little bit of a delay here. Yeah. Then yeah. Feedback part, right? And then let's draw one more. Are we drawing it correctly? I think so. Oh, okay. Yeah, we did. We missed a delay somewhere. So, And anywhere else? Yeah, no, that's, I mean, that's just on the output end. All right, guys. So let's trace this out. All of them are zeros initially. All right. Okay. I think I already gave up the first part. So, right. So 0 on the input, 0. So now this becomes 0 to 1. This shifts from 0 to 1. It propagates all the way through. So 0 to 1, 0 to 1, 0 to 1. Right. So you have an input. So request in, acknowledge in, and then request out, acknowledge out. Okay. So our input went from 0 to 1. That propagate. I mean, you'll get an acknowledge in as well, right? Remember, like that thing just goes through and all, like it fires all the way through and then comes on the output side. Okay. Of course, there'll be a time delay, right, for it to propagation delay to get through. And then let's say after that, you don't trigger your output. Okay. I mean, you don't trigger any acknowledge here. So sorry, there's no edge here. You just keep it flat. And then let's say you trigger a request. A 1 to 0 transition. Can you guys trace out what's going to happen? So let's say this becomes 1 to 0 again. Okay.
So this was one.
Yeah.
Right. So this should be the old value.
Right. Okay.
Yeah. So this is acknowledged in is the old value. So acknowledgement shouldn't change.
Yep.
Like this. And then so this is still 0.
Acknowledge in shouldn't change.
It's this is the this is 1. This is 0. Oh, so
And you had 1 before in the memory, right? Remember?
it's 0.
It becomes a 0.
It's a big thing. That's 0. No, it's 0.
Always start with like a little bit of a like it'll only become 0 after this, right? It can't become
Yeah, not
yeah. So just do elucidate that. Yeah, there we go. Yeah, perfect. Yeah, let's trace it. Do it. And then
side was 0. This is 1. So this also becomes
0.
0. Here's 0. And here 1 just becomes a 0. Becomes 0. Acknowledge out was still a 0. Yeah, so 0 and 0 should give you a 0.
The old one.
0. A 0 is 0.
Yep. It gives you unchanged. Remember, this is like this has to be like
So there's no change here.
yeah.
Oh yes.
Sorry. So did you see the request? Like, did it go through?
Yeah.
Yeah.
No.
It did go
The
through, right?
request didn't change after like
So nothing changed, right? So you have like this thing and like your request is like stayed the same, right? Now if you trigger another request, what will happen? It'll travel through, but it won't cross the stage, like the second last stage. And then after that, it'll get blocked. It'll consecutively get blocked. So first your request went all the way through the 4 stages. The second request went till here. It didn't go through the last stage. The next request will stop here. And then finally it'll just stop here. And then after that, like no matter how much you toggle your request, nothing's gonna happen. Because it's like imagine like you have like a pipeline here, or like like a pipe, and then you have like 4 stages. When you first push in something, it goes all the way to the end. If no one's like taking it, it stacks up, right? Right. So that's what this control circuitry is like really doing. So when when you fling the one side, a transition just propagates all the way through, but it needs an acknowledge backwards to clear up, to flush out whatever was there at the last. Like this, it needs to flush this out. Otherwise, it keeps like stacking up. Okay. So does that make sense?
Yeah.
Right. And you can try this as an exercise. Like keep doing different values again and again. Like you will see that eventually all of them like will just pull up unless until you give an acknowledge. But if we had given an acknowledge, let's look at the case. Are you guys ready for tracing that up? So let's assume that when we gave the first request, okay. Let's say when we gave the first request, we also gave an acknowledge for that. Okay. Okay. So what will be the value here?
So this one would be from 0 to 1.
So it'll be 1, right? I mean, it'll still retain the value, right? Like but then now when you do another request, right? This becomes so 0 to 1 is the request transition, right? And then 1 goes through, right? All the way goes through, right?
Until this point that we stopped last time.
We stopped last time, right? But now this becomes 1 to 0, right? And then 0 goes through, right? So the request comes out of the last, right? You get what I'm saying? Everyone? You guys got it?
Yeah.
Right? So only when you give an acknowledge, you're essentially like flushing this out and you're taking the new values in. Yeah, you have a question?
No, I'm good.
Okay, cool.
Um. So if like the stuff is stored until we acknowledge it, right?
Yeah.
If I wanted to reset the system, right?
If you want to reset the system,
Like you're like. Client, you just want to put anything on reset, right?
Yeah.
You have to acknowledge it to reset it, right?
no, there's okay, that's a good question. All right, guys, here. There's a good question that Robert asked as well. No, thank you so much. What's your names?
Adam.
Adam. Adam and Sinwin.
Yeah.
Okay, yeah, thank you so much. Yeah, so it's now coming to Robert's question. Really good question. So let's say you're asking like, oh, how do I like flush everything or reset it, right? Yeah, you can like your approach was really logical in terms of trying to give acknowledges. But if you give an acknowledge without a request, you also end up clogging the pipeline. Okay, so you need to strictly follow this. So if you have a pause edge, I mean, if you have like an event with a pause edge, you need to acknowledge with another pause edge. You can't like keep swinging the acknowledge line like that. That's a very strict enforcing in these asynchronous circuits. So what you do to flush out everything or reset it is just add how we have flip-flops in here. That's really what's storing the values and trying to drive out these lines, right? Just like floor them, like just connect a separate like reset line, right? And then like discharge. I mean not discharge, like pretty much zero them out, like externally. Don't mess around with the controller. Just each one will have a reset line and just like reset it. That's one way to do it. Does that make sense? Okay. Yeah.
So say we do like acknowledge the signal, like flush it out. Is it gonna flush it out like in the order that you put it in? Like, is it first in, first out? So like the first request you made is the first one that gets flushed, or is it does it pull from like the most recent request, like the last request you made in is the one that gets flushed first?
So when you flush something out through these pipelines, it's like everything in the pipeline disappears. So there's no flush in or flush out. It just like erases the whole pipeline. Okay. It's like a hazard. It's a hazard because you really have to enforce this. The moment you move out of these like the strict ordering or the transitions. So this is a transition. The original name the author gave to this is called transition signaling. Okay, because you're signaling using these transitions. So it has a very strict requirement of a pause edge event is followed by a pause edge event, and a neg edge event is followed by a neg edge event. The moment you mess that up, you have to flush out the whole pipeline, or you have to have complex circuits that handle that hazard. Usually you take a backup of these values somewhere in a shadow, like register, so-called. Shadow is just a fancy term given to duplicates of the same pipeline. And then you try to put that back. It gets dirty. But if you follow this strict ordering, then nothing gets dirty. It's chill. Okay. So to answer your question, if you have to flush out, when I say flush out, all the data is lost from the pipeline. Okay. Does that make sense?
Yeah.
Your question? You had a question? You got it? Okay. Awesome. So let's get acknowledge out.
You said it's flash out of the data stuff.
Yeah, so the thing is this acknowledge, so in this so this control circuitry, right? Let's have a sender, right? It will have a request in, R in, and then it'll have a acknowledge in, right? This is the sender, and then you have a receiver, which will have a request out, and then you'll have an acknowledge out, right? Now the thing is, what we have is this pipeline. So the purpose of this acknowledge out is for the receiver to tell the pipeline and through that to the sender that, oh, I have received the data, you don't worry about it, okay? And the thing is, this is where it differs from the conventional like synchronous pipelines. The acknowledge out that we sent, we did that, remember? Like we did like toggle this acknowledge line. Did it get through the whole thing? Like did that whip get through the whole thing? Like did that wave get through the whole thing? No, right? It didn't get through, right? So like the request got through, acknowledge just got to through the stage, just this stage. That's it. It only cleared off this stage. So pretty much like nothing happened to the master. The master already got its acknowledge the moment. So the master is only concerned, just like how in this pipeline he was only was it Albert Yeah, it was, Om was here, and then over here, Robert was there, right? And then with Albert, yeah. How Om was only concerned about, he was only concerned about Robert and not Albert, right? Do you get what I'm saying? Like that, the master is only concerned about what this first stage sees. From the master's perspective, all it sees is, like, all it shakes hand with is the first stage of the pipeline. And from the receiver's perspective, so the sender, sorry, apologies for my language. So here, what the receiver sees is literally just, the last stage of the pipeline. Okay, and everyone in between just see the person in front of them and behind them, no one else. And that's what is asynchronous over here. In case of a synchronous logic, my clock cycle for this big fat logic here affected over here stage 1, stage 3 as well, like stage 0 and stage 2, not just stage 1. You get what I'm saying? The effects on one side in asynchronous logic really doesn't get through to the other side, and that's its power. Okay, does it make sense? Is it clear? Okay, let's move on. So
Yeah.
Put the projector back on. Are you guys finding it interesting? Yeah.
I had a question about the diagram, if you can still. No, so I had a question, is also about the acknowledge out. So the initial state of the system, everything is 0, right?
Yeah.
Then when you send that request in, you set that from 0 to 1, that
Right.
1 propagates through the whole thing, everything becomes 1 again.
Right.
Then when you set that acknowledge out from 0 to 1, like, does that actually change anything? That doesn't change anything though, does it?
It doesn't change anything.
So what's the purpose of?
So the thing is, the purpose of it is that, remember when you said like we did 0 to 1 and it transitioned all the way through, right? And what were the final values this set down to, if you remember?
There's 1 on that side.
It's 1, and then this was
0 still.
this was 0, but you're saying it transitioned, right?
Yeah,
To 1.
transition.
So okay, so it transitioned from 0 to 1. Okay. Okay. Now when you send the next request, where you do 1 to 0, that's the next request, right? It propagates through, right? 0 propagates through, right? 0 comes here, right?
Okay.
This becomes 1 to 0, right? If this wasn't 1, if this was 0, will it change? Will the 0 get through here?
No. So
Right.
now it changes.
Now, yeah, exactly. So the moment you have, because you had this, acknowledge that came through,
Yeah.
it kind of cleared off this gate. Like it can get through. Same for all other acknowledges. If you don't receive an acknowledge, like it just blocks that particular stage from propagating any kind of control signals, any kind of request. Okay. Yeah, you had a question?
One is about why do you need these 4 cycles there? Why not just do with 1 or 2?
You mean like 4 stages?
Yeah.
Yeah, so these four stages, you'll see, like these are 4 stages of a pipeline. Okay, we'll come to that just in a bit. Okay,
So does the acknowledge and request, their input output,
right?
basically become like the variable clock itself? Like you know how it goes up and down,
Yeah,
and it's not exactly like what it needs to follow each other.
yeah, that's
So
it.
does it form like some variable like clock that it follows? Is
Yeah,
that the
that's-
idea.
Yeah, you're like, can we have an applause for him? Actually, because that is the fundamental. Because that's a really cool way to look at it, and that's in fact how these circuits work. In a synchronous circuit, you have like one oscillator, a common clock for all of them. Over here, the black magic that you're actually doing, I didn't reveal it, but you revealed it, which is that you're taking this, like, you're not taking the exact PLM, like you're taking these so-called clock signals and then you're localizing them, right, to each of the stage, not a global stage. So for example, this request acknowledge signals, if you see in a continuous operation of this pipeline, they'll just look like a phase shifted clock signal, right?
Yeah.
You get what I'm saying? But the only difference between a synchronous signal is that you have like things moving only on the pass edge, like activity only happening on the pass edge or the neg edge. In this case, you have activity happening on both the edges. You get what I'm saying? And these are localized, just like how, that stage's operation doesn't affect this stage's operation. These signals are just localized to each stage and not a global signal. Does that make sense? But that is really the black magic we're doing. Okay, awesome. Finally, presentation time again. Let's do it. Send to projector. Okay, perfect. All right, guys. So now, does this make sense? Everyone's with me? Let's move on to the next thing. Okay, so that's the control path. Now let's look into the data path. We can't use conventional, simple. We need to build some logic around conventional latches or flip-flops to enable data storing. Okay, and that's when we introduce the idea of an event-driven register. Okay, an event-driven register. Okay, like capture, pass. Okay, like in a relay race, you capture and you pass it, right? That's what these event registers do. Okay, it's kind of like a tiny finite state machine. Okay, don't I mean, that's just a way to look at it, but do you guys get what I'm saying? So data comes in through DN. Okay, when it's in the capture stage and it gets an event, like it locks onto the data, and then when it gets a pass signal, it gives it out. Okay, so let's look at the implementation of this. It's a simple implementation again. You build it using an XOR and a flip-flop. So there are 4 signals here.